Welcome to Design Education. We have already seen the loads and the load combinations in previous part. In this part, we will discuss the properties of concrete and steel. To continue with the same flow and understanding level, it is recommended that you should watch the part 1. If you have not seen part 1 of this video, you can watch the same by clicking the floating card above. The first material is concrete. We will see all the properties of concrete that are necessary to be understood prior to RCC design. So, let's start with grade of concrete. Concrete is known by its grade, which is designated as M15, M20, etc., in which letter M refers to concrete mix and the number 15, 20, etc. denotes the characteristic compressive strength of concrete in megapascals. Earlier, grading of concrete used to be specified in the units of kg per cm square. Now, as per the latest nomenclature, it is referred in units of Newton per mm square, which is called as megapascals. Let's look at the table in which grade of concrete is specified in both traditional and the new terminologies. If you see somewhere grade to be written as M50 or something like that, don't misunderstand it to be the high strength concrete or a typing error, but actually it will be specified in kg per cm square. You will specifically find these numbers in old edition books. Next is compressive strength. Like load, strength of concrete also varies for same grade of concrete mix, and therefore a single representative value known as characteristic strength is selected based on statistical and probabilistic principles. Characteristic strength (FCK). It is defined as the strength below which not more than 5% of test results are expected to fall. That is, there is 95% probability of achieving this strength value. Characteristic strength of concrete specimen. Test specimens are normally cubes or cylinders. In India, cube of size 150 mm is considered as standard specimen. Thus, a characteristic strength of concrete is defined as the strength of cube whose h/d ratio is 1, where h is height and d is transverse dimension. A cube of size 150 mm and a cube under uniaxial compression, which is tested at 28 days of age. From the above points, it is clear that the strength of specimen is a function of shape, that is h/d ratio, size of specimen, state of stress in specimen, and the age of curing. Next is characteristic strength of concrete in member. The strength of concrete cube does not truly represent the strength of concrete in the member. This is because we have discussed some factors above, namely the shape effect, the size effect, prism effect, which is called as h/d ratio effect, state of stress in the member, and the casting and curing conditions. Therefore, taking this into consideration, the characteristic strength of concrete member is taken as 0.67 times the strength of concrete cube. Next is design strength of concrete, which is denoted by FD. The strength to be taken for the purpose of design is known as design strength and is given by the ratio of characteristic strength to the partial safety factor accounted for material strength. The value of partial safety factor depends upon the reliability of material and the type of limit state. As per Indian standards, gamma m is equals to 1.5 for concrete and 1.15 for steel. Therefore, the design strength of concrete in member is given by 0.67 times FCK, which is the characteristic strength of concrete member divided by the partial safety factor, which is 1.5. The resultant expression gives 0.45 times FCK. Next is tensile strength of concrete. As per Indian standards, the flexural tensile strength or modulus of rupture is given by FCR equals to 0.7 times root FCK. The expression will give flexural tensile strength in megapascals. Next is short-term modulus of elasticity. As per Indian standards, short-term modulus of elasticity of concrete at 28 days of age is given by 5000 root FCK. Earlier, the expression was 5700 root FCK. The coefficient outside the radical is now updated in the latest revision of code. Next is creep of concrete. It is defined as the continued long-term deformation under sustained loading. It is measured in terms of creep coefficient. The creep coefficient is given by the creep strain divided by the elastic strain. Creep strain depends primarily on duration of sustained loading. Practically 75% of total creep occurs in first 6 months. As per Indian standards, the value of creep coefficient is specified depending on the age of concrete, and the values are shown in table as below. For 7 days, it can be assumed as 2.2. For 28 days, it can be assumed as 1.6, and for 1 year, it is 1.1. Since the effect of creep is to increase the total strength, which is epsilon I plus epsilon cc, keeping the stress value to be constant, the modulus of elasticity of concrete is reduced, whereas the modular ratio M is increased with the time. We will discuss more about modular ratio in the next session. So next is shrinkage. It is defined as the volumetric contraction under zero stress. It primarily depends on the duration of exposure. Similar to creep, it also occurs to the extent of 75% of total shrinkage within first 6 months. The shrinkage is measured in terms of shrinkage strain. As per Indian standards, the ultimate shrinkage strain is assumed to be 0.0003. If this strain is prevented, it produces tensile stress in the concrete and hence concrete develops cracks. Next is long-term modulus of elasticity. We know that due to creep and shrinkage strain, modulus of elasticity of concrete decreases. Therefore, the long-term modulus of elasticity is given by the expression shown, where phi is the creep coefficient. After knowing all these things, one question arises in mind that due to creep and shrinkage, modulus of concrete decreases. It's fine. So what? Where it is actually affecting our design? So the answer is pretty simple. As the E value decreases with time, it tends to increase the deflection and the cracking of members with time. If we look the mathematical expression of deflection, then the term E appears to be in denominator. So this change in modulus value plays very important role in the limit state of serviceability. Secondly, as modulus of concrete changes, the modular ratio also changes with time. Therefore, in WSM, which takes single value of modular ratio, does not represent the true strength and behavior of concrete members. Now, it's time to discuss something about modular ratio. We have already discussed a little about what is modular ratio. So, let me define it clearly. Modular ratio in concrete design is the ratio of elastic modulus of steel to that of concrete. In WSM, as per Indian standard recommendations, the value of modular ratio is given by 280 by 3 sigma CBC, where sigma CBC is permissible stress in concrete in bending compression, which is approximately equals to FCK by 3. But this value of modular ratio M takes into account only the partial effect of creep and shrinkage. We have already seen the expressions for short-term and long-term modulus of elasticity. So let's compare the values of modular ratios as per IS code formula and the long-term short-term modulus of elasticity. For this calculation, I have considered the modulus of steel to be the standard value equals to 2 into 10 to the power 5 megapascals. In this table, we can clearly see the difference in the values. We are using some lower value of modular ratio than what we are getting from the long-term modulus of elasticity. Now, let's move to stress strain curve of concrete. The typical stress strain curve of concrete is shown in the adjacent figure. Curve 1 is the actual curve for characteristic cube strength. Curve 2 is the idealized curve for characteristic cube strength. Curve 3 is idealized curve for characteristic strength in concrete members. And curve 4 is the idealized curve for design strength in concrete members. Idealized curves are parabolic up to a strain of 0.002 and a straight line beyond that with a constant value of stress up to the crushing strain of 0.0035. The equation of parabolic part, though it is not required to be remembered, is given by the expression given here, where the epsilon Cy is 0.002. Therefore, at the end, the final expression reduces to what it is shown here. Next part is concrete mix proportion. I have already covered that part in other video. If you have not seen it, you can watch the same by clicking the suggestion card above, or you can open the video through the link given in description box. Now let's move to the last topic in concrete as a material, which is curing period and stripping time. The concrete after casting shall be cured under moist condition for minimum period of 7 days, and it shall be kept in forms till the concrete attains the strength of at least twice the stress to which the concrete would be subjected at the time of formwork removal. In normal condition, where OPC is used, forms may be removed after the expiry periods given in the following table. Most important thing is removal of props. The props under the slab and beams shall be removed in such a sequence so as to effect the same type of structural action and support condition as assumed while designing the member. For example, the props under cantilever beam shall be removed starting from free end of cantilever towards the fixed end sequentially. Next is reinforcing steel. Reinforcing steel is commonly known by its grade and the type of bar, whether it is plain or deformed. The grade of steel is known by its characteristic yield strength and is designated as Fe250, Fe415 and Fe500, where Fe stands for ferrous material and the number following it represents the guaranteed yield strength in megapascals. Following two types of bars are available in RCC construction. First one is the plain round bar of mild steel, which is of Fe250 grade, and second is high yield strength deformed bars of grade Fe415 and Fe500. Under HYSD bars section, we have two types of bars. One is hot rolled bars and the other one is cold twisted bars, which is commonly known as Tor steel. Other properties of steel and its stress-strain relationship is very much known to everyone, and hence I am not covering that in this lecture. However, if you want a detailed explanation on stress-strain relationship of reinforcing steel, please write to me on the mail ID given in the description box. In today's lecture, I think I have covered almost all the necessary things. In the next video, I am going to cover the types of supports, design assumptions and approximations, and the calculation of loads on structural elements. Please stay tuned to get the latest updates, and if you have not subscribed to the channel yet, please do subscribe it. Thank you.